Good morning. This is Dan Steinberg at Salford Systems, and welcome to the third part of a four-part series on the evolution of regression. These slides will be available online. You'll be able to review this this presentation as a video, as well as the previous and the one to come in 2 weeks from now. So thank you again for being with us. So in the previous webinars, there were two of them. We covered the regression problem, classical regression, modern approaches, as in the MARS, adaptive nonlinear regression, the regularized regression, the lasso and the elastic net. And today we start covering a different strategy for regression model building, the regression tree, ensembles of trees, stochastic gradient boosting, and some hybrid models. We're going to refer to the Boston housing data set, and this is the data set which we will use live again in 2 weeks from now. It's a small data set, it's easy for everyone to understand, and it's the reason we chose it. Clearly, we're not going to draw any hard conclusions from results that we get here. It's strictly illustrative and interesting. So what we did last time, we ran a classical linear regression. We didn't really attempt to build the best possible linear regression model, but just running it out of the box, we got a 20% random sample test mean squared error of 27.069. We did much better, again, out of the box with a regression spline model, and the regularized regression was also able to do better, but the regularized regression, of course, cannot transform variables. So, today we're going to start with a brief overview of the regression tree. We don't have time to do a proper job of what this strategy of modeling is, so we're going to go light. And hopefully you already know, and if not, you'll be able to review some other slides and presentations we have on this topic. It is a non-parametric learning machine with the capability for both classification and regression. Much better known for classification, but it is a very interesting technology for regression as well. But it's essential as a building block for what comes after this. It's a stepwise procedure in which predictors enter the model one at a time. An important decision tree, and the one which we refer to, was developed in 1975 by Jerry Friedman, a name that is now extremely well known in machine learning and data mining at Stanford. He labeled the methodology recursive partitioning. His early work was confined to the binary target. Work around the same time by Leo Breiman and Charles Stone included regression, and the collaboration of these people after they met at a conference led ultimately to what the world now knows as the CART decision tree. The procedure works by carving a high-dimensional data space into a small to moderate set of regions, and we produce a prediction for each region. To motivate the ideas here, I'm going to start with a very intuitive and simple way of developing a non-parametric regression. Imagine that you could take all of your predictors and simply recode them so they only have two values, low and high. And then you consider all possible combinations of the predictor values. Here, there's no attempt to try to select predictors in or out. It's just whatever you've got, that's what you're going to work with. If you have k of these predictors, and each predictor can either be low or high, obviously if you can't have at least two possible values for a predictor, then it can't really participate in this process and is useless. But the k predictors will generate 2 raised to the power k possible patterns. So each pattern will define as a region, and it becomes an attractive, conceptually attractive model. The prediction of the target, conditional on the predictor values, is the mean of the target in the training data for that specific region. So here's a little exposition of that. We've got 3 predictors, x1, x2, x3. Those are all the possible patterns. We simply look to see in the training data if any of these patterns occur. If they do, we take the mean y, the target that we see in that region, that's our model. It's very simple, it's mechanical, resolves obviously all challenges that you might normally experience in modeling, such as selection of variables or functional form. The problem with this methodology, of course, is the curse of dimensionality. If you had 16 predictors, you're going to get 65,000. You probably recognize that, the 64K possible regions. If you go to 32, you're going to have 4 billion regions. And many of us work with, when we start at least, with potential predictors that could go into the hundreds or thousands. In text mining, we're going into the hundreds of thousands. We clearly can't use this methodology as we described it in order to develop a non-parametric model. So here is where trees come to the rescue. What if we were selective as to which predictors to use? And what if we could define regions with varying numbers of high-low conditions? So not every distinct pattern across all the variables would generate its own region. So the end result will be a similarly inspired non-parametric regression. We've got our regions dependent on relatively high-low definitions or regions of the predictors. But we're going to make use of vastly fewer regions, and we will never generate more regions than we have rows of data. So how do we grow this tree? The tree is grown by starting with all the training data in what we call the root node. We will look for a rule that is based on the available predictors to split the database into two parts. So the rules for continuous predictors always look like this. You take a candidate predictor and you're looking, the rule will state that the predictor is either less than a certain threshold or greater than that threshold. And we always have less than or equal to on the low side and then greater, strictly greater than on the high side. And these rules, we select rules by finding that database condition that most reduces the learned sample mean squared error. We search for all possible split points in every column of data that's available for us to predict, and then we choose the one that yields the best result, best reduction in mean squared error. So if we run our regression tree this way, using the exact same setup as we had for the previous models, the same 20% random sample for test, we're just running this out of the box with no tuning controls. We get that mean squared error down to 17.2. It's not the lowest that we saw, but it's very substantially below the least squares regression out of the box. A little bit higher than the Mars model. And we arrived at 9 regions. So there are 414 records in the training data set. So, but we had 13 variables, so there's 2 to the 13th possible regions, but we use this trickery, although very clever trickery, to get us down to only 9 regions. So let's just look quickly at the root node split so you can get your head around what it is that we're doing here. The mean of the dependent variables, 22.98. We would also show the standard deviation, but I just decided to suppress that to make this graphic a little smaller. But that's our root node. We search every one of the predictors. We discover that if we split the data into regions in which the average number of rooms in the house is more than approximately 7 or less than approximately 7, then we get 2 groups, one with a mean of 38.6, the other with a mean of 20.3. The box plots to the right show you what the distribution looks like in the root node, which is to the left panel of the graph, and then the 2 children that are generated. So that separation is clearly not perfect, but it is a nice separation, and using this strategy, this is the best that you can do. It is not possible to do any better. How do we know on the training sample? Because we searched every possible split that was available. Okay, so Friedman called this recursive partitioning, because once we divide the data into two parts, these are mutually exclusive, collectively exhaustive. What do we do next? Well, we take one of the subdivisions that we've created and we split it again. We use the exact same strategy. We do not restrict the next predictor to be something new. It could be the same predictor all over again. We could end up making several regions in the size of the houses, but we don't. Instead, we bring in another predictor. Again, why? Because this predictor is the one that reduces mean squared error in the test data the most. Okay, and then we continue and so forth. So if you follow this process all the way to the bitter end, which is something that we will want to do for our ensembles, as we'll point out in a few minutes, even the most overfit of the trees that we can generate, which yields an R squared on the learning data of 1.0. And interestingly, on the test data, it's 0.63, which is not bad, considering that this is dramatically overfit. Now we get a mean squared error on the test sample of 22.59. This was only marginally higher than the regularized regression and substantially better than the least squares model out of the box. Quite intriguing to see that a clearly overfit model can still perform this well. It's essential to keep in mind that it is a tree. An overfit tree generally does not do very badly. An overfit regression model can be disastrous very quickly and very easily. So how do we actually arrive at that optimal set of regions? Well, there's a backstepping. There's a pruning process in which we remove the weakest links on the training sample performance. We create a series of progressively smaller trees, and then we use the test sample to select the best. So we are peeking at the test sample here in order to learn something, and so that does give the reports that we have here a bit of an advantage. If you're interested in this particular technology, there are videos we have that are short, medium, and long. You can do 8 hours worth of delving into this if you'd like. So we're going to have to move on. So there's just a little exposition, a graphic that shows you how we can go from larger to smaller trees, and it's just a matter of using your arrow keys or clicking if you'd like to see the smaller trees and look at their performances. What is the strength of the single decision tree? Well, the most important ones are the imperviousness to the scalar coding of the predictors. As you can imagine, if we're just trying to divide a database into two regions, it doesn't matter how a particular predictor is coded. You could have x, log x, square root of x, x to some power. It doesn't matter. That's not going to change the rank order of the data. We're going to end up with conceptually the same split. Each of the splits only involves one predictor at a time, so therefore you're not going to be suffering from collinearity, for example, if it's extreme as a regression might. And we can't get into the details of missing value handling, but there's some elegant handling there as well. Okay, so the regression tree, as you can see from what we've shown, it was never expected to perform outstandingly. It gives interesting insight into a database. However, because it works by carving a high-dimensional data space into mutually exclusive and collectively exhaustive regions at the terminal nodes, the single prediction that's generated for a region applies to every record that falls into that region. And so, unlike a regression, unlike a parametric regression, the tree will generate this what looks like high-dimensional step function. And all the records that end up in one of the regions will have the same predicted y hat. And whereas a least squares regression will typically, if you have enough variation in the x's, will generate a unique prediction for every record that you feed to it. And therefore, it has that advantage in flexibility. So When we extract what we call the partial dependency plot for two of the variables just for illustrative purposes, we do this by simulation, and I won't go into the details now. We'll cover that maybe in the next session. But via simulation, we trace out what the model predicts for how the value of a typical home in a neighborhood in Boston in 1970 will vary as the fraction of lower socioeconomic status people varies. You get this step function with a couple of steps in it for the LSTAT variable, and for the pollution variable you get a single step function. Okay, here's a little description of what the terminal node distribution looks like between train and test, and let's skip that. If you're concerned about the fact that we only have one test partition, here we reran that analysis 100 times and allow the test partition to vary randomly. And so you see here the median performance that we get for this particular outcome now is 20, so a little bit higher, 20.66. And so here's our running score. Let's just focus on one column at a time. Now we'll focus on this 20% random test sample. It is the same for all the models, so you can see what the decision tree, regression tree is showing in the bottom row there. Okay, shortly after the regression tree gained some traction in the world of data analysis, and this is now 1980s, there was an early search for ways to make the results better. And one of the earliest ideas was to combine the predictions of several such models and to use the average prediction of these models. One terminology was using a committee of experts. And so the idea was you would somehow generate several different versions of these models, and then you would, for any record that you needed to make a prediction for, you would allow each of the experts to make its own prediction and then simply average the results. The challenge was how to generate such committees. The earliest work was actually using handcrafted different versions of these models in order to show that the ensembles had some predictive benefit. So, Leo Breiman in 1996 introduced the bagger, which has become very influential. And his idea focused on how to automatically generate as many of these committee members, committee experts for the committee that we care to use. And that's the essential trick here, is that it has to be fully automatic. And so imagine that we had an unlimited supply of data. What could we do there? Well, then we could just draw a random sample from this giant master data set. If you needed to, you could stratify the sample, grow a regression tree, now draw a different random sample, grow a new regression tree, and just do this as often as you like because you have an unlimited supply of data. How do you combine the trees? Well, since they're regression trees, very simple. Just average the separate predictions. So we usually are working with less than an unlimited amount of data. So what do you do in that case? Well, Breiman suggested bootstrap resampling, and that is sampling with replacement. Instead of extracting a record from the original training data set, we just copy it. And we can copy a record as often as we want. Typically, if we start with 2,000 records, we're going to generate 2,000 copies. Each copy is picked at random. What's interesting about this is a little more than a third of the data will not be chosen, typically, due to the randomness of the selection process, and about a quarter of the original data, of records in the original data, will be selected more than once in the construction of the new sample. So let me jump one slide and then I'll come back. At the bottom here, I show the results of a single random construction of a bootstrap sample. We started with a 2,000 record data set. Now we create a 2,000 record bootstrap sample. And the columns here represent the number of replications for records. So the 0 column says that out of the 2,000 original records, 732 are never chosen for this particular draw, but this will be very typical. Another 749, about the same fraction, will be chosen just once. And then we'll have a bunch of records that are chosen twice, 3 times. Then we tail down to 4, 5, 6. I've never seen more than 7 in the types of experiments that we've run. In the end, you end up with another 2,000 records, but what have you done with this process? By excluding more than a third of the data, which that excluded subset is known as the out-of-bag subset, we focus attention of a given tree that we grow on a different part of the data. And not only do we focus it, but we over-focus it on the parts of the data that have records chosen twice or 3 times. Now, if you did this just once, it'd be hard to justify why you'd want to do this. But if you do this many times, you are progressively focusing on different parts of the data. We once worked with a biomedical research company that was actually studying the individual trees that we were generating by the baggers. And they told us that as they looked at the trees, they could label each tree with the name of a doctor that they knew, because each tree showed a characteristic style of what aspects, what clinical data they were interested in, what was driving their own decision. And it was kind of interesting to hear that from them. So you may want to think about that as what we're doing here, this automatic generation of different personalities, different perspectives on the data. Now, one of the key things in the bagger, and this will also be true for the random forest that come next, is that for this procedure to work next, we are going to grow those very large trees. Remember, we saw that when you grow a very large tree, even though it doesn't perform as well as a prune tree if you have only one of them, but it's interesting, but it also doesn't perform very badly either, that the unpruned tree is the ideal expert that you want inside of your committee of experts. If you prune the trees, that is, if you try to make them perform better on the test data, then the committee will not perform as well as if you just let them overfit. So that was not an easy discovery to make. That took probably 6 or 7 months as Bryman was working on this particular aspect of the data, and during that time I was actually arguing with Bryman about his strategy to use tenfold cross-validation in order to decide how the committee members should be pruned. I was just concerned about how long it was taking to compute, and I was arguing with him that we should look for something that will be faster. And I had some other ideas using the OOB data. In the end, he discovered the not pruning, which is of course the fastest, because you do no post-processing of the trees. Anyway, once we've got these trees, then all we have to do is take the predictions from each one, construct a simple average, and now we're going to get something a little bit different than a single tree. We do much better on that test mean squared error. It's now dropped to 9.545. That is noticeably better than any of the other models we've done so far. This is a 100-tree ensemble. The recommended number for the bagger is actually larger than 100, but this is really already getting close to the best that we should expect, and it's good enough for these illustrative purposes. Here's just a little display of what the results would be like if we dig into the details. Uh, let's look at the first row. The actual value of the dependent variable for this row is 28.7. You can see that the first few trees are predicting low. We have a couple 23s, a 22, a 21, another 22, and then we go a little high in the 33. Well, that's just the first 6 trees. By the time we go out to the full 100 and take the average, I don't have that average for this particular column handy, but obviously what we've seen is performance of this procedure is so good that I'm sure that the actual number is very close to the 28.7 that we see there. This, by the way, is the test data set, not the training data set. Now, what I show here are the partial dependency plots, the simulations from the model for 2 predictors that came from the single tree. Let's contrast that with what happens when we use the bagger and we have 100 of these trees grown on different bootstrap resamples of the data. And you can see that the LSTAT curve is now, it's clear that there were many more splits that were made in that variable. Why? First of all, we had 100 trees, so there was an opportunity to split the LSTAT variable at many more places. And of course, each tree was grown to be very large. So therefore, there was an opportunity for that LSTAT variable to appear perhaps many times in the tree. And that would create some differences in the predictions. The NOx plot here looks kind of messy. You might even be pining for or wishing you had the old one, which is a much cleaner and simpler story. Nevertheless, this is what the procedure is giving us, which is reflecting much better the reality of the data. Okay, so here's our new running score, and you can just look at that again and look at that first column and see how impressive that bagged regression tree really is. So that moves us now from the bagger to random forest. So I'm calling the random forest the bagger on steroids. Bryman, from the get-go, I started interacting with Leo Bryman probably in 92. We talked about a great many things over the course of the years. After the bagger, it was clear that he was convinced that we could extract more out of the data, and the bagger wasn't doing it. And he was thinking constantly in the back of his mind, wondering what he could do to make the bagger better, and also running some experiments. Now, he was ultimately inspired by some work of other people, and if you look at Bryman's 2001 paper on random forests, you will see the references to the work that actually helped him crack the code of how to do this right. But Bryman was the first one to actually put all the pieces together in the right way, and then also extract the results that you could get out of the random forest fully. So what Bryman observed was that the trees generated by bagging were not as different as you would hope. Now, I gave you the example of the medical situation in which the baggers looked like different doctors with different perspectives. All that's true, but nevertheless, if you were to look at a correlation matrix of the predictions, they would be disappointingly high, the correlations between the different trees. If you look at the actual pattern of variables and how they are used in the trees, you can grow hundreds and hundreds of trees using this methodology, and probably 99% of them are going to choose that same root node splitter, which obviously is going to induce similarity throughout the tree. So how can we make them better? So what the random forest does is, just as we introduce randomness in the rows by not using the same rows in every tree, what we do is we introduce randomness in how the columns are used for model construction. But it's important to keep in mind, many people make this mistake, when we pick a random set of predictors, we don't do it once for the whole tree. If you were to do that, you would, and then do that repeatedly for different trees, you would get what's called the decision forest. But the random forest requires that you pick a new set of candidate predictors for each node in each tree. So that raises the level of randomness much higher. So what happens if we do that? Now, let's just think about what's going on here. Imagine if you go to the extreme of picking at random just one splitter for each node, then the tree is radically random. You may actually pick a variable that can't split the node at all. But for sure, that whole pattern of the tree appears to be a nightmare from the point of view of predictive accuracy. And actually, if you were to grow trees that way, their performance is often not that impressive. But if we allow a few variables to be considered at a node, so there is a little bit of optimization going on, then you can get some fairly dramatic results. So here we show some output from an RF run, and we'll have to go on to the this display here to see what the results actually are on the 20% random sample, and we get here a mean squared error of 8.2. So we've now come an awfully long way from the 27 that comes out of a regression to an 8.3 essentially for RF straight out of the box. Okay, so as you may have guessed from the comments that we were making so far, the core parameter, one very important parameter in a random forest model, is the number of predictors that you allow in the for selection. And by the way, as you probably have noticed, the bagger is just setting that n equal to all the predictors that you have. If you simply say at every node I get to look at everything, well then that's the bagger. As soon as we start lowering that value of number of predictors to something substantially less than the full set of variables that are available, then we start tapping in to the random forest methodology. So Bryman had suggested in different papers, at one point he suggested using square root of k, where k is the number of predictors that are available to you. He also suggested at other times log base 2, but ultimately you cannot guess, you cannot find a rule that will tell you how many to use in advance of an analysis. You're just going to have to experiment. But here you can see if you had 1,000 predictors, the square root rule would suggest 32 and the log rule would suggest 10. So the key for certain advantages is that the number that you use, which in our command language is called preds, should be not just below k, the number that are available, but very much below k. If you're into text mining and now you're working with a data set that has 100,000 possible predictors, you might be looking at, for example, starting with 50 or 100 of the variables at random, and then maneuver that up and down. These models actually run pretty quickly, so it's not that painful to do the experimentation. So here we show some experimentation going everywhere from one variable at random, which is the most random you can make the trees, out to 13, which is the number that are available in this particular data set. If you look to the left-hand panel and you go to the extreme left, that's using one variable, and you can see that the mean squared error, when you're using just one, is 18.12 on the test sample. So that's the left-hand panel is the OOB results. On the right hand, I don't know if we're showing it. Oh, it was actually better on the test sample at 11, but clearly not as good as possible if you were to go to a higher number. Any number higher than 1 in this display is better than 1. So here's our running score. If we do a little bit of tweaking, and here the RF tweaking was honest, we did it based on the OOB data, so we never peaked at the test date at all. We get that down to essentially 8.0. So the strengths of random forest, there are a lot of them. It's fairly robust with respect to dirty data. It's got all the advantages of a single trees. There are some nice graphical displays which aren't available at the moment for regression. They are for classification. And one of the advantages in working with wide data sets is that because you're only considering a potentially very small subset at each split, you can actually move through that data much faster than methods that require you to consider every predictor at every step. It's naturally parallelizable because so is the bagger, of course, which is a special case of RF, because the trees do not depend on each other. They can be grown in any order. If you have a cluster of machines, if you have 1,000 machines available, you can run those machines in parallel and generate as many of these trees as you like in order to generate your predictions. We can't get into the variable importance rankings in this particular session, but a number of studies and a number of competitions have shown that random forest is an extremely strong variable selection and ranking methodology. Okay, so now we move to yet another methodology that generates ensembles of trees, of regression trees, actually. And so this is stochastic gradient boosting. We call it TreeNet, and that name is now probably better known than the name Jerry Friedman originally gave it, which was multiple additive regression trees. And when Jerry gave it that name, I said, hey, you created CART, you created Mars. Calling this thing MART is just going to confuse people. We have to give it a different name. In any case, stochastic gradient boosting, mostly people now know it also as just gradient boosting, is a methodology that Jerry Friedman created in 1999. Just as a side note for creativity, Jerry Friedman is a big fan of nice beaches, and he decided that he wanted to take a year off. He moved to Australia. Sydney has a beach to the north called Manly Beach. He parked on Manly Beach, and while he was there, he changed the landscape of data mining. So maybe all of us should consider doing that if we want to make similar contributions. In any case, it worked for him. So the paper defining stochastic gradient boosting came out in 2001. Google Scholar now reports 1,600 references to it and 3,300 references to a companion paper. I'm sure the number of people that have actually referenced this paper in terms of studying it is a good 10 times larger than that. It was further extended by Friedman in 2004 and 2008 on the topics of model compression and rule extraction. We'll talk very briefly about the compression momentarily. And we, of course, have been working with Jerry on this since 2000. So, okay, we'll go here. What are the main ideas behind TreeNet gradient boosting? The first thing is, unlike random forests or the bagger, we don't work with big trees. We work with small trees. How small can we consider? Well, we can consider, and in fact very often profitably use, trees that have only one split. Fairly radical idea. The first time I heard that as a proposal, I just thought it was totally wacko and a recipe for disaster. There was no way you could possibly get very far with that, but indeed you can. So that's very interesting all by itself. Now, Jerry recommended 6 terminal nodes. After working with Jerry for now, I would say actively, because we started working also with Jerry starting in about 92. After more than 20 years of working with Jerry, what I've learned is you cannot beat his recommended defaults. I mean, I've tried a few times. I've always liked the idea of being able to show Jerry, hey, look at this, how I've improved your work. It's not easy to do. If he ended up with that as a default, it's probably pretty good. You're welcome to experiment yourself, but that's just my experience. So what do we ultimately get? We're going to get a regression, a prediction of our continuous variable, which is going to be constructed from these trees. But here's how it's going to work. The first tree, it's small, and therefore it can't do very well. That's deliberate. We actually don't want the first tree to do very well. What we want from that first tree is to just get us started and to allow us to compute residuals, which are the mistakes that that simple tree is making. And we're going to take those mistakes, those residuals, and we're going to make them our new dependent variable, our new target. And we're going to grow a second tree to predict the errors, which obviously are then the corrections that we need to make for the results of the first tree. So our new model is going to be the first tree, which is a crude approximation, and then the second tree is going to be a refinement. And the second tree could very well involve different variables and predictors than the first tree. Should we stop there? Well, there's no reason to. Once we have a new model, it makes new predictions. New predictions, unless they're perfect, generate new residuals. New residuals give us the opportunity to do yet another cycle of modeling and error correction. For a classical, statistically trained person, I would think the natural reaction would be, okay, here is a recipe for insanely intense overfitting. And indeed, it would be, unless you got certain details right, which we'll show you momentarily. Here again is just an exposition of the methodology. Each one of these trees is 6 nodes, just as recommended. The reds here are the regions that give high predictions for the dependent variable. The blues are low, and the intermediate colors are correspondingly lukewarm, for example. And so you can see that where the red occurs shows up in different places. These could be using totally different predictors in each tree. We take the results of the first tree, add the correction factors from the second tree, then add what comes out of the third tree, and so forth. So here are the tricks that keep gradient boosting from overfitting. So first, the trees are small. They're not always small, but they're typically small. Secondly, when we make that correction that comes from the second tree, we do not take the output of the second tree literally. If the second tree, for example, were to suggest that not all small houses are inexpensive, the price that the market places on small houses will depend on other things. And one of the factors in our models is the distance that the neighborhood has from the central employment center. And so being close actually makes houses and neighborhoods more valuable. So that first model, which just uses the sides of the houses and therefore says, okay, if you have a neighborhood with small houses, then we're going to predict load. The second tree could come in and say, hey, if you're close to the very close to that employment center, then we're going to predict high, and so we're going to recommend that you update the prediction by boosting it, let's say, by $10,000. Well, we're not going to take that outcome literally. What we're going to do is we're going to take that recommendation to boost the predictions for the small house neighborhoods that are close to the employment center, but we're going to multiply that recommended update by a small number, like 0.01 or 0.001 or even 0.0001. What does that do? That allows us to adapt our learning, but at a very slow learn rate, and that's key. And the larger the tree that we use, the slower the learn rate we recommend. There's also a third trick that's required here in order to keep the methodology from overfitting. Never, ever train on all of the learning data at the same time. It sounds a bit strange because we say we have a learning partition of the data. We have a test partition. You can have a third partition as well. We like the terminology learn, test, holdout. Other people use test to mean what we call holdout. Everybody agrees that learn is learn, so we're fine on that terminology. So we go to the learn partition, and then the first thing that we do is we throw half of it away. Not forever, but just for this training cycle. We make sure that every training cycle is built on a different subsample of the data. It is similar to the bagger in the sense that the bagger is always throwing out about 37% of the data and then training on the rest, but we don't then, through random draws, oversample selected records at random. We simply take a simple-minded random half of the data for each one of our trees. If you don't do that, this methodology will overfit. We do that by default, so you would have to turn that feature off in order to experiment to see what would actually happen to your models. So the contrast with a single tree is very interesting here, and it's really important to keep this in mind to understand the beauty of this methodology. Every cycle begins with the entire training data set, from which we then extract a random half. So this allows us to repeatedly go back to the root node of a tree. In a single decision tree, as you refine the model and as you bring in more predictors, you are drilling down to progressively smaller and smaller and more local subsets of the data. There is something good to be said about that. You're building very local models. The problem with the super local model is if there is an effect that is common across different parts of the tree, they're invisible to a single tree. But they do become visible when you return to the root node in the TreeNet stochastic gradient boosting methodology, and you get to start a correction model that gets to see all of the data and therefore can find these more global effects. This is just a setup slide. We're just explaining here that I'm going to grow 1,000 trees and I'm using least squares as my loss function. So this is what the results look like. Here we get a mean squared error that comes out of the optimal model, which is referring now to the test sample to see what is best at 7.4, which is a good performance. You can also see that pretty much as soon as we've gotten through the first 300 training cycles, the results are not that different. And so therefore, this peaking at the test sample is somewhat innocuous because so long as we were careful in how we set up the model, we could have done it without reference to the test sample. And I did do some experiments with the using cross-validation instead of peaking at the test sample to see what was best. Anyway, here we get a result of 7.417. So there's our running score, and you can see that the TreeNet model out of the box even did better than the random forest approach. it wouldn't have been quite as impressive if we'd used the cross-validation approach instead. How can we tune the results? Well, it turns out that with stochastic gradient boosting, unlike with random forests, you actually get a large number of loss functions. And one of those loss functions is a hybrid between least squares and least absolute deviations called the Huber-M model, which is really a blend. It treats most of the residuals in the loss function. It squares those residuals first. But for the incremental loss that comes from the largest residuals, we don't take the square. The increment just comes from the absolute size of that residual. And that tamps down the possible impact of outliers. And that often works extremely well and gives better results. And over here we see that a blend that squares only the 95% of the residuals, and then the 5% highest residuals, the incremental impact on the loss is just absolute value. That performs better yet. Let's look at the gradient boosting partial dependency plots. Those are fairly similar to what we saw from the random forest plots. So there's not a lot to choose between the two there, just a little bit more regular with the gradient boosting. One of the interesting things about the gradient boosting methodology is that you can turn off interactions. And the way in which most people have done this is by simply growing single split trees. If a tree only has one variable in it, there's no place for an interaction to actually take hold. And then since you're adding these trees together, adding trees doesn't generate interactions either. So you end up with a highly nonlinear but additive model. The performance there is shown in the bottom row. Here you can see that there's really something that is lost if you build a model without interactions. However, the loss is not that great. It's the nonlinearity which is essential, and that's most of the story, and there's a little bit that comes from the interactions. It isn't always that way. I was working with some other models that came from financial markets, which of course are notoriously difficult to model. And there we found that the nonlinearity got you essentially nothing, and the interactions, which were high order, got you everything. But in this case, it's the other way around. Okay, so we got a little bit here about interactions. Let's just go to interaction detection with TreeNet, since we're getting close to the end of our hour. And one of the things that you can get out of gradient boosting is some measure of the strength of the interactions that we can find. Here, again, we can't go into the details. We'll just show you what TreeNet will actually deliver for you. The strength of interaction is measured by the difference in the simulated predictions that come from a model that does not allow interactions versus a model that does. So it's really just a comparison of the ultimate predictions that are made and how much they differ. And a summary measure that we construct shows that the LSTAT variable is the one that is interacting the most. This report does not tell you what it is interacting with, but it is telling you that it needs to interact with something if you're going to get the best results. If you look at that set of scores here, I don't have standard errors for them. I'll show you something like standard errors in a moment. But here, you wouldn't be surprised to consider that perhaps anything from age on down is a candidate for not having any interactions, and the top few variables are the best candidates. Let me go forward a little bit and then backwards. Here, this is the result of using a parametric bootstrap to get a handle on what the variability of those interaction strength scores really are like. The blue bar is that difference between the two different ways of generating the model, and the red bar is the standard deviation. So if the blue bar is substantially larger than the red bar, then of course we have evidence that there really is some interaction going on. In the slide that I just skipped, what we're showing here is additional sets of scores that are generated by TreeNet for specific pairwise interactions. And so there you can see that what is LSTAT interacting with. The two measures, we don't have time to go into what the differences are here, but you can see that the top candidates, and there's maybe 5 variables that look like LSTAT is interacting with them to some degree, and the remainder from the pupil-teacher ratio on down, it looks like there's nothing there, and so forth. So obviously you can see how with reports like this, you could use these insights into the construction perhaps of a story or even a different kind of model that would try to embed these interactions in them. Here's an example of an interaction that was found in real-world data. It was a marketing study by one of our clients. This is the best one that I've ever seen that was discovered using this methodology. And you can see that there are essentially 2 segments in this data. There is one segment in which the relationship between the target and the predictor is downward sloping. And then there's another segment that's upward sloping. Those segments are defined by that axis which is moving away from us, that third dimension. And the entire industry was aware of the dominant pattern, and no one was aware of the other pattern which held just for this specific subset. Once they discovered this particular special subset, they changed their marketing strategy for that subset only, and then managed to change their performance with that subset dramatically, even though that particular group never responded or did the things that the marketers wanted in the way that the other group did. But it was still a way to do better with a difficult group. Okay, so we have come essentially to the end of our hour. I haven't been able to cover the hybrid models this time. I will therefore devote some time in the 4th session 2 weeks from now, in which we will spend a little bit of time at least looking at how we could get to these hybrid models in which we blend the tree method with the regularized regression in really very exciting new work, as I said, that stems from Jerry's work in 2004 and 2008. So, just want to point out then, what's next will be hands-on coverage of the same concepts that we've done now, but we'll actually be running some software live. If you haven't already done so, you may want to visit our website, download the software, which is now called SPM 7.0. This version will work for 10 days without a license. After that, if you want to run further, just request an unlock from Salford Systems, and then you'll get that 30-day unlock, which you'll be able to use to go along with us. So, I'm just doing a time check now. How are we? Oh, I'm told I have 1 minute, so what I'm going to do is simply thank you. We've gotten a bunch of questions that have been sent in. We will try our best to send individuals answers to those questions. We'll post some answers to the questions that we think would be of greatest interest to the community on our website as well. And so all that is something that we're going to be pulling together within the next 2 weeks. Thank you again very much for joining us, and we hope to have you with us again 2 weeks from now.